Another recorded class for Hydrology and Drainage Control, ENVE 670. This lecture is for the 24th of April 2019. This is our 14th of 15 lectures for the semester. Let's start with a couple of announcements here. First of all, our next class meeting on Wednesday, May 1st, that will be back to our live normal schedule, normal location, and that's going to be our final class meeting of the semester. And on that night, the homework number 12, which is related to flood control, that assignment should be uploaded to MU Online by 4 p.m. on Wednesday, May 1st. I'll send you an email with that assignment. The PDF of it is also available on MU Online. Finally, just as a reminder, the homework, the project and the final exam are both going to be on Wednesday, May 8th. And so the project is that report, the paper that you're writing on rainfall interception, and then the final exam, well, we'll have a discussion about the particulars of the final exam during our live in-person meeting on the 1st of May. Today's class is related to flood control. You can find the corresponding information in Chapter 14 of our textbook. As is noted on the homework assignment, there is a detailed tutorial on how to do one of the more complicated homework problems embedded in a YouTube lecture from a previous semester. So there will be an example in this lecture that kind of goes over the basics of it, but then I break it down in even more granular detail with some additional hints on how to solve that first homework problem in the link that's provided on the assignment.
The first thing that we'll talk about is expanding our view of storm return period. And in a lot of the analysis hydrologists do for engineering design, the scale is relatively short. You know, you're looking at maybe sizing a ditch for the 2-year storm, or sizing the inlets on a like an arterial road for the 10-year storm. At the kind of the high end of things, on a freeway, the drainage system for an interstate freeway is supposed to be designed so that there isn't standing water during the 100-year storm. And so we kind of think of that as, wow, we're really putting in a huge design. But when we are designing systems that have a huge impact on human life if they fail, like for instance a dam, then instead of looking at those return periods of 100 years or so on, then instead they consider something that's known as the estimated limiting value. And so that is kind of at the far end of the spectrum, the convergence of events that would be the largest storm that could be considered, coming from all directions, where you're assuming a really tall cloud system that has really high density of moisture, and rather than looking at the return period in terms of years, the percent of ELV, if you're designing a major structure like a dam, then you're going to be designing beyond the 1,000-year storm. Yeah.
Is it similar to the EMF?
Mm-hmm. Exactly right. Yeah. So they look at the probable maximum precipitation, and they'd find out what are the runoffs associated with that maximum storm event that theoretically could occur over a drainage basin. And so remember that the probable maximum precipitation gets smaller with an increasing size of the watershed. And the idea there is that, you know, maybe for a 1,000-acre watershed, you could expect to have pretty intense rain for a certain period of time. But now if you have 100,000 square miles, then it's unlikely that you'd have cloud cover over that entire watershed simultaneously. And so the intensity goes down and the depths decrease, but the watershed area increases. And so hydrologic design scale sometimes, you know, how big to design the system for, you know, how much extra capacity to put in a reservoir depends on the damage that it could do downstream. And so the idea is that we're going beyond the typical return periods that would be in place for culvert design or channel design. And so this table comes from your book, and it illustrates when you make that switch from looking at return period to ELV. And so even things like levees, we aren't yet at the point where we have to make the switch to ELV, but it's usually large dams where they would use the maximum value that theoretically could occur in the watershed because there is a large risk of life on failure. Usually in the case of levees, a levee failure, unless the evacuation is really sloppy, and in most cases a levee can cause property damage if it fails. There wouldn't necessarily be a loss of life like a sudden failure of a dam where you're having 20, 30 feet of water coming down a really narrow channel. Now, this table is taken from the text, and it makes the point that risk is cumulative. And so let me show you what that means. On the horizontal axis, we have the design life. And so it's how long you expect a given piece of equipment to be in service. And then on the vertical axis here is the return period. And so you can think of that as the storm size. And so look at an item that has a design life of 10 years. Now, the probability of there being a 5-year storm or larger during during a 10-year design life, you can see it's on the 0.9. And so that risk is 90% that there would be a 5-year storm or larger. So it's not a 50% risk. Sometimes we forget that risk isn't linear. You'd think, well, in a 10-year period, maybe there's a half and half chance. But for the 10-year design life, there's a 90% risk of a 5-year storm. If we go up to the 10-year storm, you'll notice, if we go over to the table there, it's 63% risk of a 10-year storm. And so even that is more than 50%. And it's because you're also including the storms that are larger than that. So 10-year storm or larger. So you're getting the risk of the 10-year storm, the risk of the 20-year storm, the 50-year storm, all of those other storms. Even though there's a smaller risk, it all adds up underneath that. So consider this. What about for a 20-year design life? So if we go here to the 20 line, what storm size only has a 5% risk of at least one event? So if you go up and you find the 5%, then you'd have to go all the way up to a 500-year storm before there's a 5% risk or less that that size event or larger is going to occur. And so what that means is that you have to consider your appetite for risk when you're sizing infrastructure. And on average, it might be that a storm comes around once every 10 years, but are you willing to accept that risk and the risk of all the other larger storms on top of it? We'll come back to this idea and to this figure when we do the specific dollar cost of storm avoidance and storm damage avoidance on Tuesday. Because when we go through those calculations, what you're doing is you're looking at how much would you have to spend in damage if a certain storm occurs. And so if you say that you're going to be avoiding the 25-year storm and larger, then you have to consider both the cost of putting that into place and also the value of avoiding that damage. So I think that probably this figure will make more sense after we start doing the calculations on Tuesday. But I did want to introduce it now just because the idea is that when you say that you're going to be providing protection at a certain level, you're protecting also against not just the storm, the 10-year storm, but if you provide protection against the 10-year storm, then that means you're also not going to have any of the damage from the 1-year storm, the 2-year storm, the 5-year storm, and so on. But it means if you're only providing up to the 10-year storm, then you are exposed to the risk of the 20-year storm, the 50-year storm, and everything larger than it. Yeah, go ahead.
Are those structures for like an ELV going to have really long design life?
Mm-hmm.
How about those dams or
Yeah. Yeah, dams are in place for 100 years or even longer. That's right. Yeah.
so it's probably not going to be good, like that you use like 10 or 5 or 2 years on that part where you have
Well, where we do use this chart and where we're designing things for 5 and 10 year, it would be flood control like levees or a diversion. There are a lot of other flood control structures besides a dam where you maybe are going to just protect against a much, like designed for a much smaller storm. So you're right that the dam, because the consequences of failure are so expensive and so risky to human life that you just design that for anything that can be thrown at it. A lot of other, we call them structural measures, we know that they're going to fail, and we just have to be picky about when it fails. You're trying to balance the cost of implementing flood control with the value of the protection that it's providing. And so you don't want to, you may remember from engineering 222 or 221, the benefit cost analysis, where you want to spend as much money as you can where you're getting more than $1 of benefit for every $1 of cost. But then there comes a point where, like Huntington's flood wall, for example, there are probably some neighborhoods inside the Huntington flood wall where the cost of providing the protection is greater than the value of the land that's being protected. You know, there are some undeveloped areas, for example, where maybe they thought someday this is going to be built out, but they never did build it out. So, it'd be better off to let that particular area fail. And we're going to talk about some of the structural measures today where, it would be reasonable to have it failing more often than a dam. Thinking back just to risk and statistics and probability, when we were creating intensity, duration, frequency curves, remember on the precipitation data frequency server, there are 2 options for the data that you can have it include in creating the IDF table. And one of the options is that you only have it calculate the IDF based on the one largest storm in each year, and that's the annual maxima way of looking at, if this is all of the storm data for 20 years, the annual maximum just picks out the one largest storm event during that period. And so you can see for 20 years, the one largest storm for each of the years, whereas annual exceedance picks out the 20 largest storms, regardless of whether more than one of them occurred in the same year. So you'll look at, in this top 20, that several of the storms are adjacent to other large storms. And so that throws the statistics off just slightly. And in risk, we have to consider the fact that you can't have more than a single large event in the same year. So generally, the recommendation is to use annual exceedance series, rainfall, and flow data because it's more representative. The problem, though, is that some stream gauges that really aren't sophisticated, as some, like the older data before it was common to have like electronic data logging, it was a float that, once a year maybe they'd go to a stream and they'd see how high the float got, and like the highest water would cause the float to stay at a certain part on a gauging pole. And so, the water would rise and it would fall down. And so, certain stream gauges would only be visited once a year, and they'd be looking at what was the maximum flow in that entire period before then. Or maybe the gauge is only visited on a monthly basis back then, before the electronic communications was well developed and data logging wasn't common. And so, the reason why we're even talking about this, it seems obvious that you'd want to have all of the data, and you'd choose the biggest storms regardless of when they were. But sometimes we were forced to do an annual maxima simply just because the frequency of the data gathering was less than we'd like it to be. Okay, so there are a lot of natural disasters that that people face. Tornadoes. you think about the number of people that are generally killed in a tornado. And now all of these, maybe it's a losing game to compare natural disasters, because if you're the one who was in the tornado, you're going to think, well, that was bad enough, right? It doesn't matter how many other people were affected by it. But tornadoes, it'll be really big news if a dozen people are affected, killed in a tornado. Like homes, maybe a couple of hundred homes would be really shocking in a tornado. Wildfire, the largest wildfire in California history just occurred, and I think that the confirmed fatalities are maybe around 100 at this point, but there's still a lot of people on the missing list they're trying to figure out. Earthquakes, now we're talking about an event that can affect a lot of people, but with proper engineering, with seismic codes and with good inspections, then earthquakes can kind of be, the effects of earthquakes can be mitigated quite a bit, so that it's really only the extreme, infrequent events that cause a lot of damage if the infrastructure has been earthquake-proofed. Flooding, on the other hand, is nowadays it's more predictable than it used to be. It used to be that hurricanes would come with no notice whatsoever and cause a lot of damage, but there isn't as much that we can do to mitigate the effects of flooding other than just avoiding flood-prone areas. And actually, that would probably be the best case thing, is that there's a lot of talk about how in places like Houston, people just keep rebuilding. Each time their house gets damaged by flooding, they take the flood insurance settlement and they just build the house again in the same spot. And then another few years down the line, they have to replace the home again. So the point is that flooding has the potential to cause a lot of death and destruction, a lot of property damage. It's a very costly natural disaster. One of the most notable flooding events that occurred in U.S. history was a hurricane that hit in Texas back in 1900, where there was relatively no notice at all. They obviously didn't have satellites predicting the weather back then, and they just relied on news from ships, and there were 8,000 dead. The city of Galveston in Texas has its highest point 8.7 feet above sea level, but during this hurricane, there was a storm surge depth of 15 feet. And so the city was completely leveled, and a lot of people just ended up leaving Galveston, Texas after the devastation. Actually, my great-great-grandfather left Galveston after the flood, and my family migrated from Texas to California because everything they owned was essentially washed away in this hurricane. They, after the flood, decided to put in flood walls, and you can see this seawall, the picture, maybe you can't see the date, is from July of 1905, and so just 5 years after that hurricane, they had put some structures in place to try and protect the city from experiencing those effects again. Another flood-related incident that is in my memory is when I was young, back in 1983, there was so much, it was, I guess, the winter of 83 and I think the spring of 84. It was such a wet spring because it suddenly warmed up, and this is Salt Lake City, Utah. There was a lot of snow in the mountains that started to melt suddenly when there was an early thaw along with rain. And the creeks were so overloaded and flooded that what they did was they diverted some of the excess runoff from the creeks down Main Street in downtown Salt Lake City. And so there's sandbags that have been piled up alongside of the road. You can see here's just a little wooden footbridge. They had to close off a lot of streets for weeks and weeks. And I remember going up there and looking at, this isn't a picture of me, but it might as well have been, we went and checked out the river running down the middle of the sidewalk and the road in Salt Lake City. And so flooding is obviously a big issue in West Virginia as well, where because of the topography, it's just not cost effective to do tons of earthwork to get a house up on the hillside, and so a lot of people will put their homes relatively close to a creek, and The flat areas are usually flat because those are the places that have been floodplains over the years. And when you build in a floodplain, that means inevitably there's going to be water coming there again. So flooding causes a lot of destruction. It not only ruins really nice homes, but it also can affect crops. This is showing a picture of a levee failure, damage to the agricultural productivity. When obviously when a crop gets wet like this, it's going to cause the crop to rot, but it also leaves us so much moisture in the soil, and the water table is so shallow that even the stuff that doesn't get fully submerged is going to have a much lower productivity than it would have if the precipitation amounts had been more moderate. So I kind of overdid it on all the flooding pictures. A lot of the damage that occurs with flooding is direct damage, where it is maybe structures that are having to be cleaned out, or damage to a foundation where the foundation is going to have to be reinforced. But there are other types of damage as well. Think about the uncertainty that comes from living in a flood-prone area. And so just the stress of wondering if the creek is going to come high in any given storm, or in the case of businesses who maybe would consider moving to a certain small town, but then just the uncertainty associated with, are your employees going to be flooded out and distracted? Is your own property, the factory itself, in a flood-prone region? Are the transportation networks in and out of the small town going to be cut off when there's flooding? And so those are secondary effects that can be considered flood damage as well, in addition to the direct damage that occurs. And so, there are social costs when a road is cut off. There are going to be school cancellations and inconvenience, and people can't, do the activities that bring them satisfaction and utility in their lives. And so it goes beyond just the economic effects of flooding as well. Some of the flood locations are along rivers, streams, and lakes. This is what we experience a lot here in West Virginia, and in coastal areas where they're prone to hurricane storm surge, then there's another possibility for flooding. But what they have in mountain areas are floods that come out of the mountains, and an alluvial fan, I'll show you a picture in just a moment of what an alluvial fan is. It's essentially the mouth of a canyon where all of the sediment and debris kind of becomes settled out, and that's generally a clue. If you see an alluvial fan, which is like a big mound of sediment at the mouth of a canyon, that is an area that could be threatened by flooding again in the future. There are other places where, because of sinkholes or because of a high groundwater table, that they can have flooding, so flooding in ground failure areas. And structural measures, this word structural measures it means engineered structures that control water. And so an area influenced by structural measures would maybe be a town that's downstream of a dam, where maybe the river itself wouldn't have caused flooding, but now it is at risk of flooding if the upstream structural measure fails. Or there can be some certain spots where over the years, I think the Army Corps has debated whether to divert the Ohio River to flood certain places strategically. Should we flood the cropland in a certain spot to prevent there from being flooding at the city that's upstream or downstream of that? So that would be another case of a structural measure, like a lock or a dam, influencing the risk of flooding in a certain area. Floodplains are normally dry areas that become saturated during a high-intensity storm. And if you've driven along the Ohio River, Route 2 goes through lots of floodplains. And you see it especially out by Green Bottom, because there's kind of like a persistent swampy area there. If you get up onto the hills, and you can look down and see these flat areas that surround the main river channel, and they're flat because It's just in the short term that the river stays in the main channel, and over thousands and tens of thousands of years, it's getting out into the floodplain often enough that it's kind of smoothing that land feature out and depositing silt and soil. So here's a cross-sectional view that shows the width of the channel increases with the larger storm return period. And so whereas the flow will stay in the main channel maybe up through the 2-year storm, when you have a 10-year storm, it's going to get into a wider section of the floodplain, and the bigger the storm, the wider it's going to get until you get to the base of some sort of a mountainside. Now, an alluvial fan, like I talked about before, is the mouth of a canyon, and this kind of illustration shows that typically what you'll have is a cone-shaped distribution of sediment that's being settled out. And the reason for that is that what settles first, when the water comes out of a canyon like this, the depth is decreasing as the flow spreads out, and that makes it so that the velocity is decreasing as well. So it's usually larger rocks and stones that will settle out first, because they're the ones that need the fastest scour velocity to become mobilized. But the further away you get from the mouth of the canyon, the finer the sediments are. And so the really fine silt and small diameter particles make it the furthest away from the mouth of the canyon, and closer to the mouth of the canyon would be larger materials. Now, there's some technical terms here that you need to become acquainted with, and you revisit the list of terminology that I gave you at the beginning of the semester. A lot of these words are on that list. And so the first thing that we need to talk about is encroachment. And encroachment is illegal development in a floodplain. And what makes it illegal is that it is going to increase the depth of the flooding that occurs. So look at this cross-section. The normal channel cross-section is this thick black line. And what they've done by adding in additional fill, and this house is built on some additional fill, is if this fill hadn't been there, then the water wouldn't need to get as tall during a flood event. Now, the rule is that you can only have a maximum increase in flow depth of 1 foot for the 100-year storm. And so the floodplain is just where the water would normally go during the 100-year storm. And the floodway is the place where development isn't allowed, because if you start to fill into the floodway, then that's going to force the flow depth more than a 1 foot increase. So the floodway is defined as the stream channel plus adjacent floodplains that have to be kept clear in order to keep the 100-year flood to 1 foot or less compared to the undeveloped state. So you can see that the floodplain is wider than the floodway. The floodplain is just this base flood elevation. This is where the water would have been if there was no development in the floodplain. But you can allow a little bit of development. You can only allow enough development so that this loss of cross-sectional flow area is pushing the water depth up no more than 1 foot. And so the remaining cross-sectional area that has to be kept clear is the 100-year floodway. The fringe is the area that can be built on. So it's maybe the least important of the cross-sectional area, because what we know is that there's going to be a faster velocity at the middle of the stream than at the edges of the stream, because here at the edges the depth is relatively low, the flow is close to the hydraulic radius, whereas down here in the center of the channel there's less flow resistance because there's so much of the flow area is far away from the wetted perimeter of the bottom of the channel. So the floodway fringe is relatively less important, and that's why it can be built on and still have enough capacity going through there that the depth increases by a foot or less. So when trying to prevent the depth from getting higher than it was before things got developed, there's a couple of strategies. First of all, reduce the susceptibility to flooding, and that happens by things like reducing development in the fringe, reducing the amount of impervious area in the watershed. So those are the ways to reduce the flood susceptibility. Modifying the flood means taking the water and putting it someplace else. So you can think of this first step as being prevention. The second step as being like prevention in terms of preventing the water, preventing the flow rates from being so high. Step two, modify the flood, means you're going to still have a certain amount of water and you're just trying to put it other places so that the water itself isn't in the habitable areas that have a lot of economic value. And then the third phase of floodplain management is just responding to floods, helping people. Now, of those three, which do you think has the most value in terms of like saving money, saving lives, like reducing the flood susceptibility, modifying the flood? Like if you're going to spend $1 to try and do the most good possible, the third one isn't public awareness. It's just like handing out blankets and shoveling mud out of people's front yards. Right. Yeah. If you do the first one, you don't have to do the others. The problem is what's the most visible? The most visible thing, like what gets on the news, isn't some nerdy engineer sitting at a desk doing calculations of, wow, we got to reduce impervious area. Like that's not going to be on the nightly news. But what is going to be on the nightly news is video of people like shoveling out their front yard, or people sweeping out the mud from their living room. So the problem is that people don't like spending money to reduce risk. It's not sexy. People don't understand risk. It seems like, why would I spend money I have to prevent damage that isn't there yet? It's like an abstract thing that's going to be in the future. So people don't like reducing risk, spending money to reducing risk. It's just, it seems imaginary to most people. And so one of the problems with floodplain management is that the most important thing you can do of reducing the risk of flooding is the least understood and, I don't know, the least appetizing for people to spend their money. People feel better, like I'm helping my fellow man if I give you money to rebuild your house. But that's not preventing the problem, and that's not like reducing the effect of the problem. So the point I want to make is that the things that have the most value sometimes are difficult to get the public to buy into because it's abstract and challenging to understand the nature of risk. The National Flood Insurance Program is a federal it's a federal program that's sponsored by FEMA, and it's an optional insurance program where people pay into a flood insurance pool, and then when they have a loss, they can get a claim filled from the federal government. And in theory, what it's supposed to do is it's supposed to encourage responsible development by charging higher flood insurance rates in places that have more risk. But what they found is that it's just chronically underfunded, that they're not collecting enough in premiums to pay out the claims that they've got. And so people, because they're not paying the true value of the insurance coverage that they get, are prone to rebuild in the same spot where they've experienced a loss. And so there have been a few like NPR stories lately after the flooding in Houston. Anytime there's a major hurricane and like a coastal storm surge, this gets in the news again, that the National Flood Insurance Program kind of has created the wrong incentives for people. It's creative incentives rather than to be responsible in developing the floodplain. It's incentivized people to build in places that are dangerous. The National Flood Insurance Program is set to require permits for development in flood hazard areas. In practice, there's a lot of development that happens that's like unlicensed and unregulated, and I can think about on my drive home, I go through a pretty rural area where a guy has set out a sign that says fill needed. And so anytime there's construction, or like even the highway department dumps their like leftover asphalt in his yard, and he just kind of pushes it into the creek because he wants more space to like park cars, and I don't know. Everybody just wants a bigger yard, and the way that he's getting, I ought to take pictures because that'd be a great illustration. I'm sure you've seen it. People they dump soil into the creek, and now they've got more flat land. But the problem is that then that's reducing the flow cross-sectional area, and it pushes the water depths higher. So in theory, the National Flood Insurance Program is supposed to force counties to have a floodway manager, and Cabell County does have a manager who gives permits for things like alterations to creeks and putting in culverts, and people are supposed to apply for permits when they develop in flood hazard areas. The National Flood Insurance Program also is supposed to encourage the use of flood-resistant materials for building, and you do see this actually more than used to be the case. There are a number of new condos and like multifamily homes being built, I've noticed in Milton, where they have a garage underneath, and all of the living space is up above a pretty tall garage. And the reason for that is that the garage is just full of like cinder block construction. It's relatively flood resistant. They're not putting in a lot of like drywall, and they're not keeping the furnishings down below, so that if the water level does rise, they can hopefully park their cars somewhere else, move to higher ground the vehicles, but then the habitable section of the structure is above the base flood elevation. Columbus?
Especially in Hilliard. Because like they're building on Columbus.
Mm-hmm.
Starting to do a lot of like the bigger townhouses, not necessarily apartments, but like the bigger townhouses that your garage is in your house.
And those are, I guess, probably close to the river, right? Because I mean, Columbus isn't particularly flat. I mean, there's a fair amount of relief to it.
In Hilliard, it's not really near the river.
Hmm.
I don't know why they're doing that, but I mean, like my mom's townhouse, like the garage is pretty much.
Mm-hmm.
I mean, hers necessarily, but it's a bigger townhouse, but
Mm-hmm.
smaller ones within the same subdivision, the garages are now under the apartment.
Yeah, I think probably they, in some places, are doing that just to economize on space, and other places they're doing it specifically to avoid flooding. And on Route 2, I noticed last time on Thanksgiving as I was driving north on Route 2, there's like some tiny house over on the left side of it. Have you seen that one? Yeah, I want to get a picture of that because it's elevated, and I think it's because they're right next to the river.
The girl that we went to, I went to school with, that's who he's building it.
Oh, really?
Yeah, she wanted a teeny house, that her parents were building her a teeny house.
Yeah, it looks pretty cool, but
Very high. It's like
it's,
Yeah.
yeah, it's really tall.
it's random.
So, no, it's the perfect illustration of having the lowest finished floor above the base flood elevation.
I'll send you the pictures of it because it's on my Facebook.
Okay, yeah, do. I'll put it in here as an illustration. You know which one I'm talking about then. Yep. Yeah. So the other guidelines of the flood insurance program is that the waterways should be regulated, and you should try and relocate people when possible. If someone is going to do really expensive improvements to their house, the flood insurance program will increase the flood insurance rates to kind of make the point that there are certain places people shouldn't be building homes, and prohibiting encroachments is the biggest part of the flood insurance program, like preventing flooding. You don't want to just allow people to rebuild, but this is kind of like the carrot and stick approach. This entire flood insurance program is, on the one hand, you're providing insurance to give people like monetary compensation if they're harmed, but then the stick is that in order to be eligible for that flood insurance program, areas have to follow some of these other guidelines of things that will reduce the frequency and reduce the amount of damage that occurs. So what we're going to do for the rest of class today is talk about structural measures. And structural measures, it's not like steel, concrete, not that kind of structural. We just mean like engineered approaches to reducing the damage of flooding, reducing the risk of a certain depth of water occurring in a certain spot. And there are 3 graphs that illustrate the effect of every structural measure. And so regardless of whether we're talking about a levee or a diversion or a dam or like a pond of some sort, all of them can be sketched out and understood according to, first of all, the relationship between exceedance frequency and discharge. And so you would make this curve, you'd figure out, what sort of a storm is going to give you a certain flow rate. So imagine that you had a WMS model for a certain watershed, and you ran the model for a 2-year storm, a 5, 10, 15, 20. So increasing exceedance frequency and increasing discharge. And it may not be linear. It could be, and probably would be, curved. But the point is that there's, for every watershed, some sort of a line that shows what flow rate you're going to see for a certain size storm. The next way that you understand how to change the risk of damage is by doing a hydraulic analysis that says, for a certain flow rate Q, how deep is the water going to be in the channel? So whereas you'd use WMS and set up a hydrologic model like HEC1 or TR55 or maybe National Stream Flow Statistics, that's how you'd come up with this curve. The hydraulic analysis curve, you'd use HEC-RAS. And so HEC-RAS is a program where you build the geometry of a channel. You're telling it how wide the river is, the side slopes. You're telling HEC-RAS the Manning's N value, the roughness associated with the materials there. And then you send a certain flow rate through the stream, and it'll tell you what is the depth for that flow rate. So here we have, at a variety of increasing flow rates, how deep the water is going to be. And then the final relationship that you have to have is an economic model. And the economic model is someone goes out into a community and looks at how many houses are there at a certain elevation and what's the value of those houses. And so the graph is stage, which is the flow depth, and then the cost of damage that's going to occur at a certain depth. And so what you can see here, this curve is saying that if the water gets up to maybe 4 feet above base level, then there's going to be a certain amount of damage. And if it gets up to 5 feet above the base flow level, there's going to be even more damage. And so, there may be certain areas that just have only cropland, and so that curve would be relatively flat, where there's not as much damage. Or it could be you have really expensive homes or a lot of built-up industrial and commercial areas that there's going to be a lot of damage. So you have to understand the hydrologic model, a hydraulic model, and an economic model to know overall what a certain structural measure is going to do and how it works to prevent flooding. So structural measures are flood control facilities, reservoirs, diversions, levees, dikes, channel modification, meaning like dredging or widening a channel. Anything you can do to reduce the risk of flooding and the economic impact of flooding. A non-structural measure is anything you can do to modify the economic relationship. So ironically, structural measures means making changes to these first 2 figures. Like reducing impervious area is a structural measure, or dredging a channel is a structural measure. But a non-structural measure is anything you can do to change that stage damage relationship. And so it could mean like jacking up a house onto stilts, even though you'd think of that as like a structure. They call that a non-structural measure because it's not related to the channel. So the decision that has to be made when you're trying to mitigate the effects of flooding is, whether it makes economic sense to do one or both of these or either of them, because sometimes the cost of making the change is outweighed by the value of it, and so you should do that. But sometimes the cost of the structural measure isn't justified by the reduction in the risk. So we're going to go through a few of these, and this will be on the final exam. I'll ask you to sketch in how a certain structural measure affects the flooding and the risk of damage. And so the point is on this slide is that it doesn't make sense just to look at it. You kind of have to draw along with what we're going to be going through to really understand how these flood control measures work. And so take a reservoir as an illustration. Let's say that you have a stream and you put in a reservoir adjacent to that stream as though it's kind of like a pond. And so here's a top view. You have a river and you've got some place where you can take the water and it's just, you can divert some of the flow into a reservoir. It's similar to that Japanese, you know, the underground facility where they're using those jet turbine engines to put water in there, the underground vaults temporarily. So what does the reservoir do and what the reservoir doesn't do? So it's not changing at all the relationship between how deep the water, if the water gets to a certain depth, what's the damage going to be? Because, you know, the city is still at the same place it was before. And when you build the reservoir, it's not like you're putting flood-resistant materials in the low levels of the houses. You haven't done anything necessarily to change the relationship between the water depth and how much damage occurs at that depth. And you're not changing anything about the channel. And this one in the middle, the discharge versus stage, is saying for what flow rate, how deep is the water going to be in the channel. Instead, what you are changing is for a certain size storm, how much flow is going to be in the river, because you have the capability of storing some of the water outside of the channel. And so what you can see is that the original curve for the exceedance frequency, it's saying that for maybe we go up here, like a 50-year storm. Originally, for a 50-year storm, you'd have this much discharge, but the flood control reservoir brings down what the discharge is going to be because you're bypassing some of the water from getting into the river by temporarily putting it into the reservoir. So you can think of the flood control reservoir as kind of being like a pond. Now, down here in the low range, like what they're suggesting is that you're going to have actually an increase in the discharge that you'd see for a certain exceedance frequency when you build the reservoir. I'm not actually sure what the rationale is there, but I think for most of the larger storms, the reason that, like, how you're reducing damage is that the flow going to the river is going to be less than it would have been if the reservoir wasn't there to temporarily hold on to some of the flow. The stage and discharge can be altered by erosion and sediment deposition. And like anytime you have a pond, it has to be maintained because if you have turbid water that's suspending a lot of sediment, because the water is moving, it can keep particles suspended. But when the water slows down, like inside of a reservoir, then the particles will settle down. And so this bullet point is that you have to keep an eye on the maintenance of the reservoir, because if you have the sediment settling down inside of the reservoir, then that could actually cause the stage to get higher for a certain discharge if it was in line, like if the reservoir is in line with the stream that the flow is going through. And if you put in this reservoir and then people get too relaxed about construction, then you could, over time, your curve of damage versus stage could get even worse if you built higher value things closer to the stream. And so just by making one change, that shouldn't necessarily make everyone feel like they have permission to develop the floodway or to put high value things in flood zones. So that's just an illustration of a reservoir. And usually reservoirs are suitable when you have the damageable property spread out over a wide area. And most of these flood control measures go in one of two directions. Either you're trying to keep all of the high value things enclosed by an area that's not going to be flooded, and so that is keep the water out of a certain area, or the reverse of that is you're trying to get the water to go into a concentrated zone, and that's what a reservoir does, is that the place that you're trying to protect is spread out over a wide area, and so you're trying to concentrate the water into a different spot. And so that makes a reservoir suitable for when the property that you're protecting is distributed. And it provides a high degree of protection. It can be used for a variety of property types like agricultural land, structures, anything that can be built where the water is not going to be. One of the benefits of a reservoir is that if you're concentrating it into a certain spot like this and retaining it, it can be stored for other uses like irrigation. And the limitation, though, is that it can't be used in highly built-up spaces like in urban areas where there's not land area available. Like in Japan, they had to do really expensive underground excavation because land area is at a premium, especially in and around Tokyo. And so, a surface reservoir is going to be a lot cheaper than an underground reservoir, and a surface reservoir like this one isn't going to require a lot of energy to get the water out of it when it's time to empty it, like those jet turbines in Tokyo were. But the bottom line is that it's suitable in places where the cost of construction is going to be less than the value of protecting the damageable property. Okay. Diversions are similar to reservoirs in that they're not changing the relationship of damage and depth. They're not changing the relationship of what flow rate is going to cause a certain depth, but what they are changing is for a certain size storm, how much flow there's going to be. And so here, what this diversion is showing is that you can have increasing size storms. Maybe we'd take this as the 10-year storm. For the 10-year storm, there's going to be a certain discharge, and remember the solid black line is what it was before this measure was put in place, and the dashed line is after the structural measure. So for like a 10-year storm, there's a certain flow rate that's going to go to the channel. But if you're diverting any excess flow over and above that, you see that it looks like maybe between the 10-year and the 20-year storm, all that extra water is being sent somewhere else in the diversion. And then after the capacity of the diversion is exceeded, then the curve is actually steeper than it was before because there is going to be maybe spillover from the diversion. Like if it's totally full, then that would cause the curve to be steeper. So you're rerouting and bypassing the flood water around damage centers. So a diversion, if we're going to sketch out like a schematic of what it would be, is maybe we have a way of sending only some of the flow through a canal or a pipeline. So usually this diversion wouldn't be used. But when the water level is going to get to, and this is like the city, when the water levels would normally get high enough that it's overwhelming this channel, then by having the ability to send some of the flow around the city and diverting it, then you'd still have, let's say, normally you could have, that's weird, 20,000 CFS maybe is a maximum capacity here, and if you had all of a sudden 25,000 CFS, you'd still have 20,000 going through the main channel, and then 5,000 CFS going in this diversion. And so there's going to be a point where if 5,000 is the maximum capacity, and now if we have 30,000, you'd still have 20 going through the main channel, 5 through the diversion, and then the other 5 is going to cause flooding into the city. So diversions are similar to reservoirs, but the idea is that you're just rerouting the water rather than storing it.
I understand like the steps because you have so much field there, but I don't understand the steeper slope. Because
Yeah.
you know, have more coming in because you have to flood back.
Yeah, so what this is saying is that once the diversion is full, then the excess flow is going to accumulate faster than it did before.
I don't think that would ever be faster than the diversion at all.
Let's think about that. Let's think about that. So it's going to say that the discharge is getting higher than if it wasn't there at all.
There's a delay, so like what's coming through the diversion.
Maybe like supercritical flow, that all that's coming through.
Maybe. Yeah, maybe.
But it's not like you're getting more water and stuff.
I think you have to think about the area under the curve, maybe, because what we're saying is that once the diversion fails, it's not still working at 5,000 CFS. So, like, I guess what it says is that, you know, like all of this is being rerouted, but once it begins to fail, then some of its previous capacity is lost. So I guess what it says is that, you know, like once this gets to 26,000, then we still can't get 5,000 CFS through this channel. I mean, that would be the argument of what that graph is saying, is that once you get beyond the capacity of the diversion, then its capacity doesn't stay at of what its maximum was, but its capacity is actually getting lower. And I'm not sure what, yeah, in the original channel. Yeah, I don't know. I mean, you could argue that it would be flat. I think the main part of it is just that the discharge, this flat part is that you can have increasing storms, but the main channel isn't carrying any more flow. Yeah.
You can, I wonder if this is relatable to, like, let's say you're at a stoplight and the cars are stopped, right? As soon as it turns green, you're going to try to speed up more than you normally would to get up to the speed that you're going to take.
I like it. Yeah.
So I wonder if the flow's doing this.
Maybe that's what the author was thinking. Yeah, I'll take it. Okay, diversions are similar to reservoirs, and so a lot of their suitability is similar to reservoirs as well. The suitability of a diversion is when what you're trying to protect is spread out over a wide area, and you want a high degree of protection, variety of types. All of the same restrictions apply for a diversion as apply for a reservoir. Levees and flood walls, though, are quite a bit different. Yeah, do you have a question?
Consider like spillways and diversions. It's not really protecting a city, it's more protecting the dam telling.
No, I think what all of these share is that the structure in question is intended to reduce the amount of damage that's incurred for a certain size storm. And so, like, of the three curves, remember we've got three models. I'm glad you asked that because I should have done a better job explaining like how the models tie together. So we've got the hydrologic model feeding into the hydraulic model, and that feeds into the economic. Okay, so the hydrologic model says for storm X, what Q? And hydraulic model says for Q, what depth? So we'll say Y. And the economic says for depth Y, how much in dollars loss. And so in the end, what we're saying is that we want to know for a storm size, how much damage. When we tie all of those together, we're saying like 2-year storm, how much damage, 5-year storm, how much damage, and so on. And so a spillway at a dam, it prevents the dam from failing, but they don't put the spillway on specifically to reduce the amount of damage, like the dam itself, like the entire dam, the spillway, like the structure as a whole is preventing the damage, but not just the individual component of the spillway. Okay, so like the diversion, how does it change the storm size versus damage relationship? Well, it doesn't change how much value is at what depth. It doesn't change the performance of the main channel. What it's doing is it's just how much water gets into the main channel. And so it's changing the Q versus storm size relationship. Okay, levees and flood walls are different because it affects all 3 of those curves. So let's look at them individually. The damage versus stage, the way it works there is that it's saying that you're not going to have any damage until the water gets to a certain depth. And so here's a picture of a levee, and you can see that there are homes that are built below the water level. Now, they're not going to have any flooding until the depth gets above the edge of the levee. But then when the water does get above the levee, then all of that damage comes in suddenly. And so they've got this initial failure where the water's just starting to slowly go over the edge of the levee, but then when it gets a little bit higher, what they're saying is you instantly get up to all of the damage level that you would have had, because all of the areas that are low-lying are going to be filled with water once that levee fails. And so how are you protecting the people? Well, number one, the depth versus damage relationship has changed. Now, the thing that's interesting is that what a levee does is it makes the discharge versus stage curve a little bit worse than it would have been. And so this is saying for a certain flow rate, the depth is actually higher than if the levee hadn't been there. And that's because you're confining the flow into a narrower area. Then, a levee is essentially you're putting a wall on the side of a river. And so you're making it so that the water depth, here's our river, you're putting a wall up so that the water is now up to this level, whereas it would have, if the levee wasn't there, for a certain flow rate, the water level wouldn't have gotten so high. So you're kind of confining the width of the flow. And so what that says is that the discharge stage curve is above the original discharge stage curve, and that's considered not good. It would have been better if, for a certain flow rate, the depth was lower. And the same thing is true with the exceedance frequency versus discharge. That's higher, which is worse, because by putting up those walls, you're increasing the flow velocity, because you're kind of forcing more of the flow to be in contact with less of the wetted perimeter, and so you're going to be having you're increasing the flow capacity of the stream. And so for a certain flow rate, the discharge could be higher. For a certain size storm, the discharge is going to be higher. It increases the speed of the water's travel, and so it's all concentrating a lot more fast. So the levee does one good thing and two bad things. Now the net effect is positive because hopefully we're only having a small increase in the discharge, only having a small increase in the stage, and you're protecting all of the area surrounding the levee. Does anybody have any questions about the levee and flood wall? Yeah, Austin?
Would it be more beneficial to kind of match the slope of curve of the levee as opposed to just putting a flood wall in that restricts the width. That way you still have your width, but you still
Yeah,
have that
yeah.
barrier.
I mean, the wider, this is not to scale, but yeah, I mean, in reality, I think, you know, like the floodplain may have several different steps to it. And they probably, your point is you want to make the channel as wide as possible. Like you wouldn't build the floodway, you wouldn't build it here, but you know, the wider you can make the channel, the better, yeah. So they want to maximize the capacity, but you know, the wider you make the levee, the less land you have for development. And so I think what they're trying to do, you know, like in the Netherlands, for example, is balance how much land they want to reclaim versus how much flow carrying capacity they need in the levee. Here's a picture of Huntington's flood wall. You know, they occasionally, I think just within the last year, they put the doors in there at the Riverfront Park. Here's a picture of the water up to the flood wall. Channel modifications is another one of the structural measures, and you can see this is a crane that's doing some dredging work in the channel. By straightening out a channel, you increase its flow carrying capacity compared to if it was meandering. And so what channel modifications allow you to do is they allow you to, for a certain flow rate, the stage is going to be lower than it was before. Like if you're excavating the soil at the bottom of the stream, you're lowering the water level because the bottom of the channel is lower than it used to be if you're doing dredging. Or if you're making the stream more narrow, you're increasing the hydraulic capacity of the channel. So for a certain flow rate, the stage will be lower. And so that's where the value is. This is the good thing that you're doing with the channel. And so, you know, if your stage is lower, then that means for a certain storm, there's going to be less damage. On the other hand, the negative thing that it does is it increases the amount of discharge that you're going to see for a certain exceedance frequency because the water's making its way through the channel more quickly. And so it's kind of like increasing the peakiness of the channel because the water can move faster. So you're decreasing the local storage inside the stream. Like if you have a meandering stream, a greater volume of water is in the stream itself than if it's a straight line connecting 2 points. And so you're storing less water in the channel, but the positive is that the depth is lower. So that's the improvement that it makes. Flood-proofing, non-structural measures like waterproofing the walls or raising a structure in place or flood warning systems that can allow people to evacuate and move their vehicles, those sorts of things, what it does is it makes it so that you have to have a higher depth of water to get a certain amount of damage. So all of these non-structural measures aren't changing the watershed, it's not changing the channel, but instead, and those are what we think of the structural side of things. The non-structural measures are affecting the damage-stage relationship. And so it's saying that you'd have to have an even greater depth of water to get the same amount of damage that you had before. Okay, we've got just a couple of minutes, and so let's take a quick look at the water.weather.gov website. I wanted to show you that here under the Water tab, this is weather.gov and the Water tab, it allows you to zoom in, and let's see if we can find the gauging station for the Ohio River at Huntington. Okay. Get close, there it is. All right. So here's the, oh, when I was hovering on it, it was bringing it up. Let's see if it'll give it to us again. Okay, so over on the right side, it's popping up the stage over the last couple of days. You can see that water levels have been relatively consistent, but they're predicting that the water levels are going to decrease. So I guess they're combining weather forecasts and hydrologic models. So it makes the river depth data available. Okay, yeah, I guess you got to double click on it. And then it has a lot of historic data here as well. So I guess we don't have any in recent history, any really notable storms. I don't know, did anybody live around here in 97? Remember a storm, a flood then? Yeah. So I think the flood wall that I was remembering, they had to put the gates in earlier this spring. So it looks like that was maybe around February 19th. It got up to 53 feet. So, and that's fairly high, but they have these different flood categories that classify, I guess a 53 would just be considered flood stage where they're having to put in the flood walls, but I don't think that it's really up to any particular height on the concrete flood wall. The other thing I wanted to point out on this water.weather.gov is there is the, let's go back again, river observations, and then there's also precipitation data here too. There's a precipitation tab where it gives you totals over the last 24 hours, and we can also go down here and have it change to like the last 7 days. And so you can see in the last 7 days here in the Huntington area, we're around, I guess, less than an inch of precipitation last 30 days. So kind of interesting. You can download the actual data for specific rain gauge, of course, but this shows you over a wider area how the precipitation patterns have changed. So if you know that your watershed is in a certain place, then you can look and see, like, remember the antecedent moisture condition. If you wanted to find out in the last 7 days how much precipitation there's been, then you could use this to model that. Let's take a look at the map service center that FEMA makes available for floodplain mapping. It allows you to generate some PDFs that are pretty interesting, where you put in an address and then it'll generate an assessment of the risk of flooding at that address. And so anybody want to give me an address, maybe your aunt and uncle or your grandparents, or here in Huntington itself is kind of boring because of the flood wall. So I wouldn't ask for your address if you live in this area, but all right. Yeah, that's a good one. All right. So you can see what it's doing is it is breaking this up into areas where it's the floodway, so close to the river. That's where they expect during a 100-year storm, the water is going to be completely inundating not only the floodway, but then you can see that there are other areas where they're designating here in the hashed kind of tannish color where there's a 0.2 annual chance of flooding. And then the areas that are shaded in blue represent where during the 100-year storm it's going to be inundated. Now the PDFs that you can generate, all right, so let's do dynamic map. Hopefully this will load. It's creating what's called a firmet. And the firmet is a PDF that you can save that has all of the definitions built into it. It's got the location. So here's the address that's identified, the key, and if we wanted to print that, then we could make a PDF out of it. So that is how you generate a firm. And on the assignment, I ask you to address to look up a couple of addresses in Milton and try and understand how they're different. You know, they're kind of varying proximity to the river in Milton and have different levels of threat assessment. Now, what I had to remove from this list of websites, in the past, FEMA had really easy access to the flood insurance rates, where it was pretty simple to calculate what the flood insurance premiums were going to be for a certain classification. But they've taken that off of the FEMA website, and now if you want to know what the flood insurance rates are, you have to get a quote from some of the, I think they have servicing companies that actually collect the premiums and process any sort of claims. But the premiums can vary quite a lot, where a home that is outside of an area that's designated as flood prone, and so here in these unshaded areas, the flood premiums could be, you know, maybe $500 a year, whereas if you're living in these areas that are flood prone, the premiums could be $4,000 a year. I mean, it's really about an order of magnitude to live in the area that is inside of the 100-year floodplain versus outside of the 100-year floodplain. So it's kind of interesting how much it changes. All right, so that map service center is something that you're going to have to use for the assignment. This picture of flooding is from in Louisiana after Hurricane Katrina, and it shows just a bunch of wrecked vehicles, muddy sidewalk, muddy yards, and one of the problems that they had with the flooding in Hurricane Katrina was that there are a lot of toxic tailing ponds from the chemical industry in Louisiana along the coastline. There's a big oil and gas and chemical industry on the coast, and a lot of those waste ponds got washed inland and spread out over a pretty wide area. And so it wasn't just the water affecting drywall and ruined carpets that was an issue, but there was a kind of like a secondary damage in the form of all this toxic waste that now had to be identified and cleaned up. And so what this picture illustrates is the range of different categories of harm people can suffer when there's flooding. When a flood like this has occurred, then people are going to be less interested in this neighborhood because now it's known as being flood prone. And so that can lead to like a reduction in property values, and it can decrease the amount of property tax that the municipality is able to collect on people in this area if the base property values decrease as well. So the book identifies a couple of different damage categories, and direct damage is the one that's the easiest to think of. It's the damage that's caused by the water itself and the cost of repairing things that have been directly affected by the flooding. But these other cost categories of damage are a little bit more abstract, and so if you think about the business revenue that's lost while things are either shut down or underwater, or while things are being repaired, businesses aren't selling gasoline, they're not selling hamburgers. And I remember driving through the floods that they had in West Virginia back in 2016. I drove through a town that's really close to the Greenbrier. Was it White Sulphur Springs? Yeah, I was driving home from DC, and I knew there was a flood, but I didn't know like the whole town was basically evacuated because we were just looking for something to eat, and we drove into White Sulphur Springs and just nothing was open at all. And so, you know, that lost business revenue is the indirect damage of the flood, where even if someone was up on the hillside and didn't have any water damage, then they're still affected by the fact that everyone else is either evacuated or the lack of access. Secondary damage is the adverse effects of people who depend on output from a certain area. And so you may know Alcon on Route 2. It's on the left side as you're driving northbound on Route 2. And so that's, you know, adjacent to the Ohio River. So if the Ohio River got really high and Alcon was flooded, then people who depend on whatever's happening there at Alcon, they make interocular lenses there. And so I think those are like replacement lenses that go into people's eyes during surgery. And so if there happened to be some sort of a global shortage on interocular lenses because of flooding in that location, then the people who can't get what they need would be experiencing secondary damage. And so we all experience secondary damage when there's a hurricane or flooding on the Gulf Coast, because the cost of fuel goes up. And there are these periodic spikes after a hurricane or after a refinery disaster. But I mean, you can detect that there are effects due to flooding. The cost of plywall and building materials can go up when there's a lot of flooding and damage in coastal areas, and so now suddenly there's a big demand, so the supply in other places decreases, and so prices can go up. And so that's an illustration of the types of secondary damage that can arise from flood damage, where you're thinking, well, thank goodness I didn't live in the flood zone, my house is safe, but still, you know, you've got a few dollars that you're having to pay because of the secondary damage that can occur. Intangible damage is the damage that's difficult to quantify on a dollar basis. You know, these are the disbenefits where an area is muddy and smells bad after a flood. Or it could be the social well-being that's lost. You know, people couldn't go to the baseball games that they were expecting to because now they're just shoveling mud for days at a time. The reduction in aesthetic value. With driving through White Sulphur Springs after the flood, it wasn't as nice a place probably as it was before the flood. And so that reduction in the previous aesthetic quality of an area is classified as intangible damage because it's tough to put a dollar value on all of that. But then you'd think after all of these previous categories we would have exhausted all the different ways that flooding can cause damage, but there's also the uncertainty where businesses will intentionally avoid areas that are under a threat of flooding. Or if there's been a flood, then people are less willing to build there in the future. And it also limits the economic development. And so if you think about one of the reasons why West Virginia is kind of like chronically poor compared to the rest of the United States, you remember that we read that article that was saying that rivers and the overlying river and agricultural networks in the United States is part of what makes America perpetually rich. And so West Virginia is poor in both of those things. It's poor in flat land where agricultural crops can grow, and what limited flat land is available in a lot of places is immediately adjacent to streams. And so there's not going to be a lot of development in areas that are flood prone, and then everything else is like 45% slopes that's really tough to put a crop onto. And so you could say that there's some uncertainty damage that we face here in the state because a lot of the areas, we're lucky to have some flood control structure where there's dams that help to eliminate the risk of flooding, but there are still plenty of places that are affected when there's flooding. And so there's a failure to develop economically because of that uncertainty. Okay, so remember these relationships, these models that we talked about last time. And for each of these models, you need to think about what goes into the model, so the independent variable, and what comes out of the model. And so what we're going to have is the independent variable will be on the horizontal axis, and the dependent variable will be on the vertical axis. And so a hydrologic model is going to allow us to put in some return period, or in other words, an exceedance frequency, and then the curve or the sloped line, or maybe it's a flat line, but basically we bounce off of that and get a certain flow rate. And so you could prepare this curve by running WMS and a HEC1 model or a TR55 model. You could do it for the 2-year, the 5-year, the 10-year, the 25, and then you could make a curve that connects all of those flow rates. And so you'd have a different number of return periods, and then you'd have all these flow rates, and so now you've got a model that connects the discharge versus return period. And so what comes out of that is the flow rate. And then you take that flow rate and you put it into another model, the hydraulic model. And the way that you'd create this curve is you'd take a program like HEC-RAS, or you could do the calculations manually. You remember at the end of hydraulic engineering last semester, what we were doing was we were doing open channel calculations like the numerical integration method, the standard step method, where you were taking a known depth at a certain location and you were working upstream by looking at the slope of the energy grade line, the channel slope, and so you knew at a certain distance upstream what's going to be the depth for a flow rate. And so this curve is just for a flow rate, how deep is the water? and you run it for a lot of different flow rates. And so essentially, you know for the 2-year storm, how deep will the water be, because the hydrologic model told you the discharge, and the hydraulic model told you the depth. So we essentially know how deep the water will be, how often. You know, maybe once every 10 years, the water depth will be 10 feet. Once every 50 years, the water depth will be 12 feet. And then this final model, we put in for a certain depth, how much damage do we experience? And so stage versus damage. The input, the independent variable is the depth, and then this economic model, a surveyor has gone out and identified, you know, at what elevation are different structures. And then we have from the tax data the appraised value of every structure. And so you know if the water level gets to a certain depth, how many of the structures in a given region are going to be underwater from that survey. And then the economic data comes from maybe the assessor's office. And so we can know every 2 years how much property is underwater. Every 5 years, how much property is underwater. Every 10 years, how much damage is there going to be due to flooding. So the method that we're going to go through today as an example is we're going to calculate for different structural measures how much of that damage can be reduced. You know, if we have this baseline understanding of the amount of damage we're going to experience and how often we're going to have that damage, then different structural measures like dikes, levees, diversions, reservoirs, those things have a different amount of protection. And so we'll calculate how much reduction in damage each one of them provides. And then we'll calculate the annualized damage savings. And that's what makes this a little bit tricky, is there's some probability involved in trying to take an event that's only going to happen once every 10 years, and you're trying to spread the cost of that event over every year. And you may remember from engineering economy that you can have some cost that's a known present value, and you can find an annual value from that. Do you remember the time value of money calculations where you have some given P? So if P is given and you want to know A, then there are tables where you can find A given P for some interest rate and for n number of years. Maybe you remember that. Maybe you'll learn it again as you prepare for the FE exam. But what we'll do is we'll annualize the damage savings. And so rather than saying, you know, if we put in the diversion, it's going to prevent the 10-year storm. And so rather than taking that savings only one time in a 10-year period, you say, well, what's the annual value of that savings? Because it's damage that didn't occur. And so the benefit is experienced every year. It's not just experienced once every 10 years, because you don't know exactly right now, you don't know when that 10-year storm was going to come. Now, to go through that process of calculating the annual damage savings, we have to consider the incremental probability, which I think is best explained once we're actually looking at the example. But the idea is incremental probability is how much probability is there between the 2-year storm, for instance, and the 5-year storm. You know, the 2-year storm, in any given year, there's a 50% chance. The 5-year storm, in any given year, there's a 20% chance. So between those two, there's 30% of probability between the 50% chance and the 20% chance. And so the incremental probability is looking at the area under a probability curve. It's pretty abstract, but it'll make more sense as we're actually crunching the numbers. The damage reduction is looking at whether you can build a small diversion or a big diversion, which is to say, you could build a diversion that provides protection against the 10-year storm, or you could build a really big diversion that provides protection against the 25-year storm. And so not only are we comparing different alternatives, but we can also compare different sizes of alternatives, because everything's going to have a different cost. You know, the larger diversion is going to cost more than the small one. And so One of the example questions we're going to look at today is how to know how big to build something. And so to do that, you're going to look at the damage reduction that's saved when you go from preventing the 5-year storm and now preventing the 10-year storm, for example. So that's what the delta D is going to be. And then the annual expected flood reduction, what it does is it says there is a certain amount of damage that's avoided every year and a certain probability that that storm was going to happen. And so you combine it all together. You know, there was a 10% chance that this was going to happen and a 20% chance that that was going to happen, and you add up all of the things that were prevented. You know, if you're building to the 25-year storm, you're protecting against the 25-year storm, so you now can avoid the damage of the 2. You're avoiding the damage of the 5, the 10, everything below in size, below and including the 25 has been avoided. And so you get to kind of accumulate all of those probabilities and all of the costs. Okay, there is an Excel file on MU Online. It's a starting file, just so that you don't have to type all of the spreadsheet in from scratch. So go to MU Online and download that Excel file, and we'll work through it together to illustrate this example. It's at the bottom of the front page. Okay. So let's look at the data that we're given to begin this example. We have exceedance probabilities which correspond to storms of different sizes. And so, for example, a 20% exceedance probability, that goes along with a 5-year storm, because that means in any given year, there's a 20% chance that you'll experience the 5-year storm. The 10% probability, that goes along with the 10-year storm, because in any given year, there's not only a 20% chance of the 5-year storm, but there's also a 10% chance of the 10-year storm. So we are exposed to all of the probabilities cumulatively. There are threats coming from every direction. The existing condition is this is how much damage we experience in millions of dollars for a storm of a certain size. So you can see that the 5-year storm causes no damage right now. But the 10-year storm, if it occurs, we're going to have $6 million of damage. If the, let's see, 5%, that would go along with the 20-year storm, right? Yeah, 20-year storm. So if there's a 20-year storm, then that will cost us $13 million of damage, and so on and so forth. Now, one of the things that we don't see immediately is you think about like the 1,000-year storm. So that 0.1 exceedance probability, that's the 1,000-year storm. Well, $54 million is a lot, but there's only a 1 in 1,000 chance that's going to happen. And so actually, on an annual basis, the threat of that 1,000-year storm is pretty small, because the risk is spread out over 1,000 years. So when we go through these calculations, what we're going to see is it's not these really rare big events that threaten us the most on an annual basis. When you're adding up the annualized cost of damage, it's kind of these smaller and middle range storms that are providing the most risk. Because, in other words, I'd rather have a 7%, like think of it, what if you were going to win the lottery? I'd rather have a 7% chance at $10 million than a 0.1% chance of $54 million. So if you're going to look at the damage per event, we'll see that it's not these huge events that give us the most trouble. All right, so now consider there's 4 structural alternatives that are being selected, or considered. There's the dike, and the way the dike is working is that if it's in place, we don't experience the 10-year storm, and then we also don't experience this 7% storm, 7% probability. But then any storm bigger than that, it's as though the dike was never there. So we experience the full brunt of the storm for anything larger than the 7% probability. But then some of these others change the relationship slightly, like the diversion. Not only do you, with the diversion, you prevent more of the storms, like you're only seeing any damage at the 5% probability, but now it's also less damage. Instead of the 13 million with the diversion, you're only seeing 6 million once there begins to be any damage. So does everybody understand this first table? This is what's given in the top part of the example 1 tab. Now, there's 4 different alternatives, but for each one of these, it's just a certain size. It's the next example where we'll be considering different sized alternatives. So what we're saying is a dike of a certain size is going to perform this way. We could have built a different dike, like we could have made the walls higher, and if we built a different dike with higher walls, then that maybe wouldn't have had the $13 million worth of damage in the 5% storm. But this is just for a diversion of a certain size, a dike of a certain size, a reservoir of a certain size. And so what we're going to try and do is find out the expected annualized benefit. So we want to know which one is best. Of these 4 options, which one is best? Which one delivers on an annual basis the most benefit? So the first step is to assemble expected damage cost versus exceedance probability data, and that's given to you already. Now in the real world, this is maybe a table that you'd need to assemble, and so there would be a lot of work going into this, because what you'd need to do is you'd need to assess how each of these 4 structural measures are performing. So you'd need to find out, the dike, what properties are now going to be protected versus threatened when the dike is in place, the diversion, and so on. You'd have to essentially evaluate all of them to generate this data, and so it would not be negligible to prepare this table. But once you have it, what you can do is you can calculate the damage reduction versus this do-nothing existing alternative. So we're going to find out how much damage is avoided versus the exceedance probability. So let's actually do that. You can see step 2 in this table I've provided. We want to find the damage reduction compared to existing. Now, the existing isn't there because existing compared to itself is obviously 0. But I've given you in the dike an illustration of what the calculation is. It's the existing minus the dike for each one of these. And so this is how much damage is avoided if you do the thing. And so fill in the rest of the table. There's some blanks here for the diversion and the channel modification. But each one of them is going to be the existing versus the thing that's being compared. And so you subtract to fill in that table. Okay, so let's take a look at the channel modification. If we do channel modification, then it's going to save $6 million worth of damage during the 10% storm. During the 7% storm, it's going to save $10 million worth of damage. During the 5% storm, you're going to be saving $9 million. And so essentially by building this thing, this is money that you can consider as revenue or income, an avoidance of amounts that you're going to have to pay if it occurred. So any questions with step 2? All right. Now, the incremental probability. Down here at the bottom, I explain what the incremental probability is. And so I use the illustration as the difference between the 20% and the 10% exceedance probability. Then as a fraction, that's the 20 minus the 10 divided by 100. So there's 0.1 probability between the 20% and the 10% storm. And the reason why we're calculating that is we want to find out what's the average damage reduction in that increment. And so here for the dike, what we've got is this first step is between the 20% and the 10%. And so the increment is 0.1, and then the average damage reduction that I have of 3 is the average of, there's 0 damage reduction for the 20% storm, and $6 million of damage reduction if we build the dike and if we experience the 10% storm. And so the average of that increment is 3. We're just taking the simple average there. And the size of the increment here we can say is 0.1. So I've gone through all of those calculations for the dike and kind of shown the beginning pattern for the diversion and channel modification. And so for each of those remaining blank fields, calculate the delta F for the incremental probability and the delta D. Now let me caution you that this isn't just plugging numbers into a spreadsheet template. You kind of have to really understand. It's more important to understand what it means because if you have a problem like this on the exam, you're going to be reproducing it from scratch. You may have notes on your spreadsheet that says like what these steps are. But the point is just being able to find the formula and drag the formula down through the rest of the cells isn't enough to really understand this. And so let's take a moment to make sure that it kind of makes conceptual sense. Okay, I give you down here in the bottom is the sum of delta T times delta F. And so for the dike, that column should be 0.64. See if you can figure out how to do that for the diversion, channel modification, and reservoir. What you're doing is you're summing up each of the individual delta D times delta F. Okay, calculating this is tedious because what you have to do is you have to multiply the 3 times the 0.1 and add it to 8 times 0.3 plus 5 times 0.02, 0 times 0.03, and so on. So you have to, first of all, multiply them all together and then add it all up. And so the formula is going to look like this times that plus that times that plus this times that. So we're multiplying them together and adding them to sum it up. And then let's see, if I anchor all of the references in the A column, then I'll be able to drag the formula to the right. So let me go through and press F4 for all of the references to the A column. Okay, it's all anchored. Fingers crossed it works. All right, so 0.640 million, and we'll talk about what that is in just a minute, but to drag that sideways now, it looks like the best option is the reservoir, because you want the most damage reduction. So how much of this do you get to credit every year is what the delta F column is calculating. So in any given year, you're going to experience 10% of the $3 million savings, because that's like the size of that probability on an annual basis. And in any given year, you get to take 3% of the $8 million savings, because the $8 million savings doesn't occur every year, but we want to know the annual damage reduction. So this is going to be the annual expected benefit from the damage that is avoided. And so to annualize these, we're having to consider the incremental probability, which is the size between different storms. In the end, you can see that the one with the highest annual expected benefit is the reservoir. So this sized reservoir is going to save every year 1.378 million. Now we don't know how much this reservoir is going to cost on an annual basis. If the cost is more than $1.378 million, then you may have to reconsider whether to build it. Of course, remember that it's not always just the direct costs that should be considered, because we were talking about the direct cost of flooding, but then there's also some of those secondary effects, like the reduction in people's willingness to develop an area, the secondary damage for people who are inconvenienced when there's the damage. And so if we could somehow work those fuzzier, more difficult to quantify factors into these reductions in damage, then that may increase the savings even more. So if you lose track of how this works, I've tried to put as good an explanation as I can here at the bottom. And this is an example that comes from the textbook, though it was a rare example that I feel like the textbook really dropped the ball. It just didn't explain it in enough detail to make it clear what was happening. So are there any questions on this illustration? I think that for the homework assignment, you're doing basically the same thing. And I think that on the homework assignment, I've given you a link to a video. Is that right? Like on the equation, on the homework assignment page. Where's that? Yeah, so You may want to take a look at that video over the long run. It would probably save you time to watch that if it's not immediately obvious what you need to do. All right, so I alluded to the fact that this is only calculating the benefits, but we also need to factor in the cost of providing certain levels of protection. So before we move on to this next example, are there any questions about this one? All right. To maximize benefit, you minimize your cost. And cost is coming from two things. The cost is coming from the damage, and it's also coming from how much you pay for a certain level of protection. And so that's the total cost. And the approach for whether to build a diversion that protects against the 5-year storm versus the 10-year storm is you add up the costs, each of these two categories, and you find whichever has the lowest. And whichever one has the lowest is also going to be the one that maximizes the annual benefit. And so the annual benefit is thought of as the savings compared to the flooding with no structural measure in place. And so the net benefit would be the difference between the reduction in damage and the cost that you're paying. And we'll look at each of these categories as we work through the next example. But before we do, consider this figure. What this is showing is, first of all, this is the damage, the curve that speaks to for a low probability event, there's lots of flood damage cost. And for an event that happens frequently, like maybe the 2-year storm, there's less damage cost associated with that. So this curve is saying it's the costs related to flood damage. And then the other component of total costs is the cost of building things to prevent the flood damage. And so that's what this first cost curve is. And so the design level, if you're going to design against a really big storm, then your first cost is going to be high. And you can expect that the damage cost you're going to experience with a really high design level. So if you're building a really sophisticated structure that will protect against the 100-year storm, for example, now you're not having very much damage cost, but your construction costs are high. And so this total cost curve, what you should be doing is working to minimize the total cost curve, so finding the lowest point in here. It's similar to in engineering economy when you do a cost effectiveness analysis where you're trying to minimize the annual expense. You're picking how long to own something or which level of construction to do by the overall lowest cost of ownership. And so using a car as an analogy, you can buy a car that costs very little now, but then it's going to take more in maintenance and repairs as it's being used. Or you can spend more now, and there's going to be less of those maintenance and repair expenses. And so you want to balance that idea of spending a lot now and less in the future. You need to balance with structural measures. You want to balance not providing too much protection where the first costs overwhelm the damage, but trying to balance the both together to minimize the risk. Okay, now this is another example that comes from the book, but it takes a lot of staring to kind of figure out what they are talking about in this data table that's provided. And so here's how I think to interpret this table. What we have right now is a system that's providing protection against the 5-year storm. We don't have to spend anything to get the existing level of protection. But on average, right now, with the 5-year storm protection that we've got, we experience $1.94475 million of damage per year. So that is the amount of damage that comes to us from all of the storms that's larger than the 5-year storm. So remember that even if you provide protection against the 5-year storm, you're still threatened by the 10, the 25, the 50, and all of those other big ones. And so what this annual damage represents is all of the storms that are larger than the row that you're on. So if we have 5-year protection, we don't have protection against all these other storms. Now, since we already have 5-year protection, it costs you nothing to get it because it's already owned. But if you were willing to spend $0.2 million per year so that you have protection against the 10-year storm, then what that means is that now you're only exposed to damage from all of the storms bigger than the 10-year storm. So you're threatened by the 20, the 50, the 100, and so on, all the way down through the list. And so what that means is if you spend $0.2 million per year, now your annual damage is only $1.64475 million per year. So already we can tell that's a good deal because you're spending $0.2 million a year and you've just reduced your flood damage from 1.94 to 1.64. So in other words, you spent $0.2 million and then you reduce your damage by $0.3 million. And so the rule is you should always spend the additional dollar if you're saving more than you're spending. So should you spend $0.2 million to save $0.3 million? Absolutely. So keep buying the next largest alternative until the incremental cost outweighs the incremental benefit. Then you shouldn't build the next level down. So what we're going to do is we're going to analyze this situation to figure out how big should we choose. Should we choose the 10-year? Should we choose the 20-year? Should we choose the 50-year level of protection? And that example is on the second tab of the template file that I provided. And so what we're going to do is calculate the total cost, which includes both the damage and the cost of providing protection. So these two columns can be thought of as the two curves that make the total cost curve. So there's the cost of constructing the structural measure, and there's the cost of the damage. And so we want to know the total cost by adding these two columns together for each year. And then the benefit is going to be the reduced damage compared to the existing protection. And then we also want to do the net benefit. All right, so that is here on the example 2. So the total cost you can see is the damage and the annual cost together. So we'll calculate that column down. The benefit is the difference between the annual damage from the existing condition and the annual damage of the row that you're on. And then the net benefit is the annual benefit minus the annual cost. So how big should we build this, what was it again? It's a dike system. Well, if we want to maximize the benefit, that tells us that if we build protection against the 50-year storm, then that's going to minimize the damage. Compared to every year having $1.94 million worth of damage, we're only going to have $1.649 million worth of damage. And to get that big reduction in damage, we only have to spend $1 million per year to do it. And so the total cost, where you're adding together the damage expense and the annual expense of having that dike system in place, you're going to have to pay something. You can either pay for the flooding, you can pay for a dike, or some combination of the two. But this is the one that has the minimum cost for each year.
This is only direct cost, right? It's not really looking at direct cost.
It depends on what's going into these damage estimates. I mean, in this example, it doesn't really specify in the book, but let's just pretend that it's including the direct and indirect costs. And that those have been realistic estimates, because you can goose the numbers any way you want. Like if you say that it's worth $1,000 an hour not to have to shovel mud out of your front driveway, then, then it's going to seem like you should build the biggest dike in the world. But here, the biggest differential between the cost and the damage reduction also corresponds to the largest net benefit. So the net benefit is saying the difference between the benefit and the costs. And so it's like you're, compared to the baseline situation, you're coming out $295,000 per year ahead, because this is in millions. So if you find someone to finance this for you, like a bank, or you can take out bonds to build the structural measure, then it's essentially free money. Then you're saving $295,000. Now the other thing to keep in mind is that the people who are threatened by flooding may not be the same ones that are being asked to pay for the cost of the structural measure. So if you live up on a hillside in a town and the people who live in the low-lying areas are trying to get everyone to chip in equally, then that's a bad deal for you because you're not going to be enjoying the direct benefits of the flood reduction. But you know, there are all those secondary factors where if you can't drive through the roads and if your grocery store is underwater and your employer is underwater, the fact that your house isn't directly in the floodplain is great, but it's not like you've avoided all of the damage altogether. Okay, well, one last thing I wanted to show you was some pictures that Ashton provided me with of that tiny house that's being built out on Route 2. So, you know, this approach to avoiding damage is just that you figure how high is the water going to be, and you make that lower level of the structure unoccupied space. And so that's going to be maybe where tools or cars or vehicles are, and then it's only the upper part of the structure that's going to be habited. And I wish you could get a sense of how small this actually is. It maybe doesn't seem small, but you kind of get a feel for it. If this is the width of a door, then the house is only, what, maybe like 6 times wider than a doorway. And so by having relatively flood-proof building materials like cinder block walls down beneath and then not having any of the OSB or wood until you're at the elevation that you wouldn't expect to see water very often, then it's kind of a smart way to use land for residential use that otherwise is too risky to build on, is just elevate the structure.
And that's Route 2 to the right of that structure.
Mm-hmm.
That little white gravel area, that's Route 2 back there.
Yeah. The interesting thing is, like, so what if the flooding happens at night? It seems like they're going to have a boat, you know, like up in the rafters, because it would be easy to get isolated, right? And maybe, you know, well, there's only a 1% chance the water is going to get any higher than than this level, but still you're stuck. You know, like if the water's just up to here, the top of the garage, then you're going to have to canoe back to civilization.